Have you ever stopped to wonder if there's some kind of secret rule, a master key that governs every single division problem you can possibly think of? Well, today we're digging into exactly that, a simple but incredibly powerful idea from ancient mathematics called Euclid's division lemma. We're going to break it down and run it through 5 clear examples to see how it all works. So let's just start with a really big question. What if there was one single, elegant formula that could predict and explain the result of any division? I mean, it sounds almost too simple to be true, doesn't it? But that is precisely what we are looking at today. And there it is. A equals BQ plus R. Now, I know it looks super simple, but this little equation is that universal blueprint. It's the engine that's been running in the background, defining how numbers relate through division for more than 2,000 years.
Okay, so we've got our blueprint. But, a blueprint is useless if you can't read it. We need to know what each part of this machine actually does. So let's break this formula down piece by piece.
Think of any division problem like a short story. And in every single one of these stories, you've got 4 main characters: A, B, Q, and R. Let's figure out who they are and what roles they play in this whole thing. This formula is really just a secret code for something we all learned back in grade school. A is simply the dividend. That's the number you're starting with. B is the divisor, what you're dividing by. Q is the quotient, the main answer. And R is the all-important remainder, the leftovers. All right, now this formula comes with one absolutely critical condition. It's a simple rule, but it's the thing that makes the entire system work with perfect, predictable precision every single time. And it's all about that remainder. So here's the golden rule. The remainder, R, has to be 0 or a positive number. But, and this is the most important part, it must be strictly smaller than the divisor, B. This one little restriction is what guarantees that there's always a unique answer. For any division problem, there is one and only one correct quotient and remainder, and this rule is why. Okay, enough theory. We have our blueprints and we have the golden rule. It is time to fire up this engine and see how it handles some actual numbers. Let's run it through its paces with some examples. First up, 25 divided by 4. We know that gives us a quotient of 6 with a remainder of 1. So in Euclid's format, that's 25 equals 4 times 6 plus 1. Now, does our remainder fit the rule? Yep, 1 is greater than or equal to 0, and it's less than our divisor, 4. Perfect. Next, let's try 37 divided by 5. That's going to give us a quotient of 7 and a remainder of 2. So we write it as 37 equals 5 times 7 plus 2. Let's check the condition again. Is our remainder of 2 between 0 and 5? Yes, it is. The rule holds true. So what happens with a perfect division? One with no leftovers, like 48 divided by 6. Well, the remainder is 0, and this is a great test for the lower limit of our rule. The equation becomes 48 equals 6 times 8 plus 0. And sure enough, 0 is greater than or equal to 0, and it's less than 6. So even when there's no remainder, the lemma is perfectly satisfied. How about 29 divided by 4? Well, the result is a quotient of 7 and a remainder of 1. The equation, 29 equals 4, times 7 plus 1, is super straightforward, and that remainder of 1 is well within our bounds. You see? It's this rock-solid consistency that makes this whole concept so incredibly powerful. Okay, our final example is really cool because it pushes the rule right to its upper limit. If we divide 63 by 8, we get a quotient of 7 and a remainder of 7. Now notice how the remainder, 7, is just one shy of the divisor, 8. It's as high as it can possibly go, but it still remains strictly less than 8, which means it perfectly follows the rule. So, we've seen it work with small remainders, with 0 remainders, and with remainders that push the very limits of the rule. So, what's the big picture here? Let's zoom out for a second and really understand the pattern and purpose behind this unbreakable rule. When you see all 5 examples laid out side by side like this, the pattern just becomes crystal clear, doesn't it? This isn't just a series of happy coincidences. What we're actually seeing is a fundamental truth about how numbers work. For any 2 integers, there is always one unique solution. So why does all this matter? I mean, what's the point? Well, this lemma isn't just some interesting little observation. It's a foundational tool. It's the essential first step, the key that turns the lock, for a powerful process called Euclid's algorithm, which happens to be one of the oldest and most efficient ways to find the highest common factor between 2 numbers. And this brings us to a final, really thought-provoking question. If a simple rule about leftovers can be the key to solving ancient problems like finding the HCF, what other complex challenges, from modern computer science to cryptography, are just sitting there, waiting to be unlocked by this exact same fundamental principle?
This explainer was based on material from KSV Academy Olway, who are empowering students in mathematics. Thank you so much for watching.